In yesterday's class, we studied electric field, we studied dipole. Today, we'll study Gauss law, potential, and we'll try to study capacitance as well. Is it okay? So, the first thing we'll do is Gauss law. Before doing Gauss law, in fact, I would discuss with you electric flux. What is electric flux?
Passing through a given area when it is say perpendicular to the direction of flow.
Phi, you said, is equal to number of field lines. Huh? Q upon epsilon naught is Gauss law, it's not flux. You said it is number of field lines?
Passing through a given surface when it is held
No,
perpendicular to the
it's
direction.
proportional. You cannot count field lines. Please note, if I draw 3 field lines out of a charge, it doesn't mean it would produce only 3 field lines. It's a diagrammatic representation. The field lines are not a real world entity. However, flux is a real world entity. So it is proportional to the field lines, not exactly equal, proportional to the number of field lines passing through an area perpendicularly. Is it okay? So flux mathematically is E dot dA, d phi, through a small surface. Why I am taking it as a small surface? Because let us say this is the small surface. You know area vector, if field is like this, you can take any direction of area vector, any of the two perpendiculars, okay, for an open surface. So the area vector is like this, flux would be this. Is it okay? As shown. Why I am not writing this like this, I will tell you in a moment. So let's discuss flux cases, all the possible cases of flux. The first, what does N denote? N is a number of field lines passing through an area perpendicularly. Let's say this is the area. So number of field lines passing through this area perpendicularly. Okay? Okay. So phi is not equal to N, it is proportional, because you cannot count the field lines. Okay? So it indicates, it's not equal, it just indicates the number of field lines passing through a surface perpendicularly. Exact value is always given by this, the dot product. So let's have some cases for flat surfaces. For flat surfaces and E vector constant. What does it mean? That field has a uniform magnitude and direction. Okay, field has a uniform magnitude and direction. So for these kind of cases, phi would be integral d phi. Okay, phi would be integral d phi, because for small element we know. Just a second. Okay, sorry. So for a small element, flux is this. So for larger area, we can find the flux by adding the flux through small elements, which is the process called integration, right? So we would be integrating it, but in integration, the task is easy. Why? Because E vector is a constant. Constant things are brought out of integration, they no longer participate. So flux here would be E dot A. So only in this case, when field is constant and when area is flat, only in this case would the flux be written like this, E dot A. So this is the kind of scenario. This is the kind of scenario. The area vector would be along this direction, and this is the angle between them, theta. Okay, not in every possible case. The second case is if the surface is non-uniform. If the surface is non-uniform, I mean like curved, or the field is not constant, or both. Okay. before I go with this, try to understand what I am going to do here. Let's say you have a hemispherical bowl and the field lines are going like this. Okay, I hope you understand this, that if I am drawing parallel lines, equidistant lines, parallel and equidistant lines, it means uniform field, right? But you know, for all the portions, this small portion would have area vector in this direction, this small portion would have area vector in this direction. All these portions would have area vector in different independent directions. You cannot find field using this. In which direction would you take the area vector? However, this is a hemispherical bowl. Okay, so the number of field lines going through it would be as good as those going through this small surface, this flat surface. Okay, पूरा बाउल में से उतनी फील्ड लाइंस जाने वाली है जितनी इस सर्कुलर सरफेस से जाएंगी, राइट? नंबर ऑफ फील्ड लाइंस गोइंग थ्रू द बाउल, द हेमिस्फीयर would be equal to the number of field lines going through this circular surface. So I can anytime replace the curved surface with a flat surface. Okay, so this, for this the flux would become, this is E would come out and this is dA vector and this is E dot A flat portion. Okay, area, this is the area of flat equivalent. Okay, so you can replace, this is the area of flat equivalent. Okay, you can anytime replace a curved surface with a flat surface, okay, such that the number of field lines are same. Okay, so the third would be for E equal to variable. Okay, E not constant. When E is not constant, so you can check that flux is E dot dA. Now whether the surface is flat or curved, if field is not constant, different field lines would make different angles with area vector. Here this is the angle, here the angle is 0, here the angle is this, right? Different portions would make different area vectors, different portion would make different angle with area vectors. So we cannot separate E and dA. We cannot separate E and dA. Why? Because E dot dA is actually E dA cos theta, and since cos theta is varying time and again, how can you pull E out or cos theta out? Is it okay? You cannot solve it any further. You need to integrate itself. Okay, you need to integrate it. So this has to be left here. ठीक है, shall I erase it? Now tell me, it is an easy one, don't write it. just verbally tell me. This is a sphere, okay, a closed surface, and it is kept in uniform electric field. What would be the flux through it? ये यही बताओगे? Zero? नहीं? Don't you think so? Field lines entering and leaving, entering and leaving. So flux through a closed surface is zero until unless it is having some charge inside. Obviously, then it won't be zero. So you can, make it as your fourth point for a closed surface. ठीक है, not having any charge inside, phi is equal to 0. ठीक है, for straightforward. Electric field constant हो नहीं हो, it doesn't matter. Okay, it doesn't matter. Flux would be 0. एक ही साइड जा रही थी ना, यहाँ they are entering and they are leaving. They are entering and they are leaving. तो दो अलग अलग सेंस में, एंटरिंग को हम लोग नेगेटिव ट्रीट करते हैं एंड लीविंग को हम लोग पॉजिटिव ट्रीट करते हैं, ऐसा ही होता है. ठीक है, एंड एडिशनली मैं यहाँ बता भी देता हूँ, एक क्लोज्ड सरफेस के लिए हमेशा एरिया वेक्टर कैसे लेते हैं? आउटवर्ड. ये कन्वेंशन है. फ्लैट सरफेस के लिए कैसा भी ले सकते हो, दोनों में से कोई एक परपेंडिकुलर ले सकते हो. फॉर क्लोज्ड सरफेस एरिया वेक्टर इज ऑलवेज आउटवर्ड, अवे फ्रॉम द बॉडी. तो अगर फील्ड लाइन यहां से एंटर कर रही है तो यू कैन अंडरस्टैंड दिस इज एन ऑब्ट्यूज एंगल, फ्लक्स नेगेटिव, और यहां से लीव कर रही है तो फ्लक्स पॉजिटिव. सो एक्चुअली दैट्स हाउ इट कम्स आउट टू बी 0. ओके, हर फील्ड लाइन पहले एंटरिंग के टाइम पे फ्लक्स नेगेटिव प्रोड्यूस कर रही होगी, ओके, एंड लीविंग के टाइम पे फ्लक्स पॉजिटिव, राइट? क्या? नहीं, हाफ वाले में आगे वाला ओपन है, फ्रंट सरफेस इज ओपन, इट्स नॉट क्लोज्ड हेमिस्फीयर. क्लोज हेमिस्फीयर कुछ ऐसा होता, मतलब मुझे शेडिंग करके बताना पड़ता. आई वुड हैव शेडेड इट कि द सरफेस इज क्लोज्ड. तो इट मींस इधर से एंटर करती फील्ड लाइंस और इधर से लीव करती, तब ये होता क्लोज सरफेस होता तो फ्लक्स 0 होता. चला है? So now let's discuss Gauss law. It states that flux through a closed surface, I use E dot dA, you can use E dot ds, it doesn't matter. Okay, area vector can be represented by dA vector as well as ds vector, doesn't matter. Okay, is equal to charge inside by epsilon naught. ठीक? Charge inside by epsilon naught. This is what it said. Now let's discuss the details. Let's say this is a surface. You have one charge here, 1, -2, 3, right? Okay. This imaginary surface is called a Gaussian surface. Okay. So for applying Gauss law, you need to imagine a Gaussian surface, right? And for us, Gaussian surface would be, as per the need. Is it okay? So Q1 minus Q2 and Q3. These are the charges. Let's pick a point P. At this point, the field would be because of all the three charges. Here, everywhere the field would be due to all the three charges. So LHS side, in LHS side, E is due to all charges. Okay, but in RHS you can see only the inner charges are considered. So flux would come out to be Q1 minus Q2. This is flux, right? Flux through closed surface. Flux through closed surface. Okay. So upon epsilon naught. Okay. So while field is due to all the possible charges around, flux is due to only the inside charges. Is it okay? Okay. Outside charges will not contribute to the flux through the surface. So it's like flux due to Q1 and minus Q2 is equal to flux due to all charges, because the third one won't contribute, right? But E due to Q1 and minus Q2 won't be equal to E due to all charges. Okay. Field is not same, but flux is same. How? Discrepancy hai na thodi. The problem is, let's say initially you had only two charges. There was some field distribution. When you brought this third charge, this charge altered the field distribution, but still the number of field lines coming out of the surface or entering into the surface remains the same. Is it okay? Okay. So when you bring outside charges, they disturb the field arrangement. That's why we say, okay, the field is because of all the three now. Okay, because Q3 would always contribute to some field. It would disturb the arrangement. That disturbance is its contribution. Is it okay? That disturbance is its contribution. So when you bring outside charges, they contribute to the field. Definitely contribute to the field. Right? No, it won't be same, definitely. So if you are saying that, let's say we have a sphere, here inside a charge Q1 is kept, you found the field here to be E is equal to K Q1 by R square. Now you bring a charge Q2 here and you are asking me whether the field here would be same? No, absolutely not. This charge will disturb the field here. Okay. Now because the the field distribution will not remain symmetrical, you cannot apply Gauss law here. पहले तो ऐसा था ना? Earlier it was like this. Field distribution was very symmetric, right? Equal field lines everywhere, very symmetric kind of arrangement. Now when you bring this field distribution would bend away. So it would be something like Q1 here, with Q2 keeping its field in this direction. Right? With Q2 keeping its field in this direction. So Let me count the lines: 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7. So two more lines. Number of field lines produced by Q1 would still remain same, but the distribution has altered. So since the field is not symmetrical, you cannot apply Gauss law, right?
But in this case, area will also reduce.
नहीं, area तो it's like free hand drawing, छोटा बन गया. I didn't, the area of the sphere is not reduced. It's just that while drawing it, I made a smaller sphere.
Number of lines through which they are passing, that area also will reduce.
No, here the field lines are congested. Area of the sphere will not change actually. Through the same area, now more number of lines are passing on this side. Here, less number of lines are passing through this region. So the distribution is disturbed. I am not drawing any field line here. Doesn't mean that the field would be exactly zero. Field would be exactly zero at a point where E1 is equal to E2. The field, because of both, would exactly cancel each other. Only at that point. Okay? I'm just showing that comparatively here, very less number of lines would exist. The field would be very low. That's it. Right?
So does this painting of the field line depend upon the charge of the second charge which we have drawn?
Yeah, exactly. If it is bigger, they would bend more. Okay? Please. Yes. If Q2 had been negative, then the field lines would have bent toward Q2. Okay, some of the field lines would have started terminating on Q2. Rest all would have gone to infinity. The field between these 2 points won't be zero when the charges are opposite. Okay, I'll elaborate the question. She's asking, what if Q2 is negative? Would the field be zero anywhere? It won't be zero in between the two charges, but it may be zero, away from Q2 or away from Q1, depending on which one is bigger. Okay, so it would be, if Q2 is bigger, field would be zero somewhere here, away from Q1. If Q2 is smaller, field would be zero somewhere here, away from Q2, right? So I hope you have all drawn this. हो गया है ना? So let's continue then. You already would be knowing this is a cube. A small charge is placed at center. What would be the flux through each of the face? Each of the face. Yeah, q by 6. है ना? What if this charge is placed at face center? Small charge. Have you studied solid state in chemistry?
We started.
So it would be q by q by 12. अच्छा q by 2 would be for half. नहीं अभी कह नहीं सकते, यू कैन नॉट से अपर एंड लोअर तो नहीं कह सकते. देखो इफ आई से चार्ज इज प्लेस्ड एट सेंटर, रुको, इफ आई से चार्ज इज प्लेस्ड एट सेंटर ऑफ फेस, इफ आई ड्रॉ अनदर क्यूब,
It will be shared by.
it would cover the charge completely, enclose the charge completely, and Gauss law is valid for charges inside. Okay, so which means these two cubes would be sharing the charge equally. So flux through one cube would be q by 2 epsilon naught, one cube. What about any side? There is a problem here. For this, the field lines would be somewhere like this, going like this, ऐसे, right? This side, okay, this which I am darkening. For this face, what would be the flux? कुछ होगा? For this face, we can find the flux, it is 0. Why? The field lines would be either parallel to it. समझ आ रहा ना? It is a flat surface, charge is situated at center. So either they would go down or they would go up or they would travel parallel. Is it okay? Either they would go down or go up or travel parallel. Is it okay? ठीक है? Okay, they would not cross the surface, so flux would be 0 for this. Only for this. We cannot find flux for rest of the 5 faces. Why? Because now different faces are at different distance, so we cannot, judge the distribution of field lines. We cannot judge the distribution of field lines. Is it okay? Okay. So flux for this surface would be 0. Flux for the cube would be q by 2 epsilon naught. That's all we can judge. How it is? Same charge shared by 2 cubes. So for one cube, half charge is available. For other cube, another half is available, right? What if I, these are all NCERT like questions. Okay, you have them in NCERT. But it is just that you never went beyond. इसके आगे तो नहीं सोचा ना कभी? I place a small charge at corner. What about the field? What about the flux now? अच्छा, सबको solid state आता है chemistry में. It would be q upon 8 epsilon naught. So flux through cube would be q upon 8 epsilon naught. Now we have 3 faces. This corner is shared by 3 faces, face number 1, face number 2 and the rear face, face number 3. Okay? Place a charge at the corner of this room. So you can see the corner would be shared by the roof wall, this and the side wall, front wall and the side wall. For these 3, the field lines would be somewhere like ऐसे जा रही है, going like this, always grazing the surface, not actually entering. How can it enter this surface? It would definitely not do like this. So the field lines would enter only through the corner, they would not enter through any of the face. So what would happen actually? For 1, 2 and 3, the 3 faces which share this corner, for these 3 faces the flux would be 0. So flux 1, flux 2, flux 3 would be 0. What about the rest 3? For these actually it is very handy if we have a model, and I don't have a model right now. Okay, so if you could just find a model, it would be a great help. Absolutely correct. For rest of the three faces, okay, again imagine a charge at this upper corner of the room. So for three faces, this upper corner is shared by roof, the flux through the roof is 0. It is shared by the side wall, the flux through the side wall is 0. And it is shared by the front wall, the flux through the front wall is 0. We have three faces remaining, the floor, this wall and the rear wall, back wall. The room is a cuboid actually, but for a cube, all the three faces would be of equal size and all three faces would be equidistant from the corner. So all three faces would distribute the flux equally. Is it okay? This actually is a JEE question asked long back, but this is a JEE question. They asked this, not q by 24 epsilon naught, because that's easier to think. It's difficult to think that for these faces the field would only graze. It cannot enter, because for entering you need to have a loop banana. Like it cannot make this loop banana type of thing. It would rather go straight. Okay, so flux through the remaining 3, 4, 5 and 6 would be equal, that is q by 24 epsilon naught. Okay, q by 24 epsilon naught. Okay. Now a question for you. A line charge of linear charge density lambda passes through a cube. ठीक है? What could be cube of side L? What could be the max flux through the cube? Okay, line charge is passing through a cube. Line charge समझ आया? Wire having charge. Okay, charged wire is passing through a cube. What could be the maximum possible flux?
Passing through the center.
There can be so many ways passing through the center. In which orientation?
Sir, I'm asking that the wire is passing through the center or is diagonally?
Wire passing diagonally.
Diagonally.
Exactly. कुछ समझ आया? Put the wire along the diagonal. In that scenario, it would carry maximum charge inside. Okay, it would have maximum charge inside. So in this scenario, the length would be L root 3, length of the wire. The charge would be lambda into L root 3, and the flux, maximum flux, would be lambda L root 3 by epsilon naught. Now this was an easy one, right? Let's have a better one. a line charge is passing through a hollow sphere of radius somebody asked how flux equals q by 24 epsilon naught. We left that question. I'll come back. I said that same charge is shared by 3 faces. So for those 3 faces, the flux would be, the field lines would be parallel, grazing to the surface, right? I would have to draw the surface again. See, it's a 2D board and it's not very convenient for me to show how. You need to have a Rubik's cube kind of thing, okay, for which you can see. For this surface, for upper surface, field lines would graze like this. They would keep on going like this. They are not entering, they are actually grazing the surface. Any line would enter if it goes like this, into, but field lines would be grazing, traveling parallel. Or they would enter, because they would definitely enter, because what is happening? 1/8 of the charge is inside the cube. So the portion inside the cube sends the charge in the sends the field lines in the cube, right? Okay. I was saying the portion of the charge inside, only 1/8 of the portion would be inside. You can refer to solid state for this. Solid state topic has been taught to you in chemistry and it is exactly the same question. Okay. In a cubic lattice, the charge is placed at corner. So how much charge is shared by that cube? 1/8 only. So only 1/8 portion is inside and that 1/8 portion would send the field lines inside like this into the cube directly, not through the faces, because that portion is inside already. So usko it needs not send the charge through the faces, it is already inside. So it will send the charges, send the field lines inside. For the faces, top, front and side faces, top, front, actually it's the rear one, for us it's the rear one, the back side wala face and the side face. For these 3 faces, what would happen? The field lines would go parallel like this. So no flux through these 3 faces. For the remaining 3 faces, flux would be evenly distributed. Why? Because from one corner of the cube, this face, the center of this face is at some distance, the center of this face is also at the same distance, and the center of this front face is also at the same distance. These 3 faces are equidistant. So that's why flux through these 3 faces would be evenly distributed. So while the flux through whole of the cube is q upon 8 epsilon naught, flux through these remaining 3 sides, 1, 3, 1, 2 and 3 is 0, while 4, 5 and 6 it is 1/3 of this, q by 24 epsilon naught. Okay, so I hope this is clear now. I'll come back to the question I was writing. A line charge is passing through a hollow sphere of radius r, comma, at a distance x from center. Flux through sphere would be, it is some kind of arrangement like this. Okay, the question didn't give the figure. It is I draw it because so as to help you. The actual question didn't have any figure.
So whenever some lines
it should be mentioned like that.
सिर्फ passing हो like पहले वाले में भी सिर्फ
नहीं,
passing है.
इसमें what could be the maximum flux it said. That's why we took the diagonal orientation. इसमें the orientation is already given.
So but you said that the in the original question
Sorry. Just yeah, what?
so you told that in the the original question did not have the figure.
Yeah, but it clearly said there is a hollow sphere of radius r. The line charge is passing at a distance x from center. So distance x from center. It's not the maximum charge inside wala situation. If I wanted maximum charge to be inside the sphere, I would have sent it through the diagonal, right? It would have carried maximum charge inside. Acha, I forgot to tell you the field, the charge density is lambda, linear charge density. ये तो it was obvious, right?
So सिर्फ line charge पे आ रहे हैं.
नहीं हुआ होगा, है ना? Draw a radius r. This portion L would be how much? Under root r square minus x square. The total length of charge inside would be 2L. So charge inside would be lambda into 2L, which is lambda 2 lambda under root r square minus x square. So flux would be 2 lambda under root r square minus x square by epsilon naught. It was an easy one, I guess. Let's extend this. An infinite sheet of charge density sigma passes through a sphere of hollow sphere. समझा? Infinite sheet है इस time. It's an infinite sheet. It is passing through an imaginary sphere. So imaginary sphere, it is like cutting the imaginary sphere into two unequal parts. करें? कुछ हुआ? Anyone? हो रहा है. So it's like something, this a sphere, okay, this kind of thing is happening, and you know this is a large sheet, infinitely large, right? So if it passes through the sphere, it would make a cut of which shape? Knife से आप, you cut an orange, what shape is that cut? So the cut made here would be actually circular in shape, this circular cut. So it would rather cut this into two halves, into two parts, not halves, sorry, accidentally. Okay, ऐसे sheet जा रही होगी. Okay. Also, this circular portion of the sheet would be, this circular portion would be inside the sphere, right? Okay. So let's try to find out what the area of this circular sheet. I will draw it here. This is the circular sheet with circular portion जिसकी मैं बात कर रहा हूँ. Okay, of which I am talking about. It passes through a distance x. It passes through a distance x. Radius is r. What is the radius of this circular portion? Under root r square minus x square. What would be the area of this circular portion? Let's call it small r. The area would be pi r square or pi capital R square minus x square. The charge would be sigma into this thing. Sigma is what? Charge upon area. So to find charge you need to multiply it with area. This would be charge density into area. The flux would be sigma pi r square minus x square upon epsilon naught,
Epsilon.
right? That was the answer. Okay, I'll erase the left half and we'll go over to applying Gauss law. Applications of Gauss law, right? Hmm.
This would remain same for small portion also.
What?
Small other half.
Other half के लिए what would remain same?
Flux.
The flux. Actually, this is the flux produced by this circular portion on the both sides. So if you want to calculate the flux through the bigger portion, it is half of this. If you want to calculate the flux through the smaller portion, it would still be half. Okay, because a sheet would always produce equal fields on the both sides. So even a small portion of sheet would still produce field like this equally on both sides. Okay, so flux from flux through the bigger portion would be this total flux by 2, and through the smaller portion would again be total flux by 2. So applications of Gauss law, you already know a few applications of Gauss law, right? Like for a point charge you already know, for a line charge you already know. For a line charge, for an infinite line charge, lambda was how much?
Q upon 2 pi r.
Sorry, okay, I accidentally wrote. Actually, for infinite sheet we cannot calculate lambda. I was actually asking you this. This would be lambda upon 2 pi epsilon naught r. Just remember, for a finite sheet, for a finite line charge, let's say the angle is alpha here and beta here. Do you remember Ex was k lambda by r?
Sin alpha plus sin beta.
And if I extend both the corners, alpha and beta would both become infinity. So it would become 2k lambda by r, sin 90 plus sin 90, 1 plus 1, and 2 into 1 by 4 pi epsilon naught lambda by r.
Lambda.
You get the same thing. So what we did yesterday was a general case of the same thing which you know. Is it okay? Okay. The graph for this would be E R. Okay. Since it is inversely proportional to R, the graph would be like this. If the amount of electric flux entering and leaving an enclosed surface respectively are flux 1 and flux 2, the electric charge inside the surface would be, come on yaar, net flux would be flux 1 minus flux 2, and net flux is actually Q inside by epsilon naught. This is a basic question. You are preparing for JEE. You can find Q inside. So first application you already know, we just discussed, we just connected two concepts. One we studied yesterday and one you already know. Okay. Second one, for a sheet, yes.
So for line we derive formula for means infinite length line.
Mm-hmm.
That means a line behaving like infinite.
नहीं sheet नहीं, line has very large length, okay, you know, line, let's say this is the point is very close to line, the length of line is very large as compared to the distance of point, you can treat it as infinite line, not sheet, not sheet, okay. Line is thin. For sheet, you already know, you take a cylindrical Gaussian surface and things would have remained same if you had taken a cuboidal or cubical whatever Gaussian surface. So how do we pick the right Gaussian surface? That's the point. Here also it was told cylinder hota hai, khatam, bas, cylinder hota hai na? Why cylinder? Why not take a cube here? Okay, so something like this. ठीक है, you know cylinder होता है बस. Why take a cylinder? Why take this kind of surface here? See, Gauss law is a universal law. It is valid for regular, irregular, any type of surface. Okay, closed surface, not valid for open surfaces. Okay, any type of closed surface. But the problem is that if the surface is regular, if is irregular, if E or dA or the angle between them is varying at every other point, then how will you be able to add all these quantities? Integration is what? It is a process called addition. It is an addition process, right? You won't be able to add, because if things are varying rapidly, how would you be actually adding each and every element? Calculating the flux through each and every element and adding? Impossible. That's impossible, right? So we need, you know, some arrangements. Gauss law would still be valid for any surface, but we cannot use it. We won't be able to use it. It's our limitation. अपने बस की नहीं है, right? Okay, our limitation. So what we do, we apply it for symmetrical surfaces. What do you mean by symmetry? Symmetry simply means that magnitude of E should be same at all points, or it should be 0. If it is not same at all points, it should be 0 at some points where it would be different, or E should be perpendicular to dA vector. These are the points to be considered. So either the magnitude should be same, or the angle between E and area should be 90. Okay, the dot product should be 0, so that you don't have to calculate it actually. Is it okay? Why we chose cylinder? Because the line is at axis, you know, it's through the middle of cylinder. So at every point at every point the electric field would be same. Every point on the cylinder electric field would be same magnitude wise. Direction की बात नहीं कर रहा हूँ मैं. And what about the direction? The direction would be along the area vector. Okay, so we choose surfaces where either E is perpendicular to dA for some portions. Okay, I will summarize everything instead of this. How to choose surface? How to choose surface? First point is either E should be constant, magnitude should be constant, and theta should be 0. Either this, some portions of the surface should have this, or the some portions, other portions should have theta 90 degree. This is the direct criteria. So all points on the curved surface have same magnitude and the angle is 0, while all the surface on all the points on flat surface have area vector and E perpendicular. What about this kind of arrangement? On the curved surface, you know, this is perpendicular, while on the flat surface all points are equidistant from the sheet, so they would have same magnitude. Okay, okay. So symmetry is how is symmetry determined? That okay, all the points on a surface should be equidistant from the charge. All the points on this surface are equidistant from the charge. On this surface are equidistant from the charge. Okay, means everywhere E, magnitude of E should be same. In those kind of scenarios, actually when E dot dA you are calculating, it actually becomes E dA, angle 0 hai, so cos 0. You can bring dE out because the magnitude is constant, you can bring it out. You can always bring out constants from integration, so you would be able to integrate. That's how we pick. So let's check how well you pick. You already know. I'll draw the graph for this first. You know the field is, sorry, E is sigma upon 2 epsilon naught. You already know this, and we, you know, did this yesterday as well when we were discussing disk. We did this yesterday as well. So this is E versus the distance r. So constant field positive side, constant field on the negative side. Why negative? Because it is leftward. So vectorially it is negative. Is it okay? If we if we had chosen cube instead of cylinder for infinite sheet, all these points would have been equidistant. Still it would have worked. It won't, cube won't work for a line charge because the corners would always be at more distance from the middle portions. So field would not be same. Symmetry means all points equidistant from the charge. Right. So let's come back. We can choose? No. Infinite line, you form a cube, corners are far away, middle portions is nearby. Okay. So third one, you know, for a hollow sphere, है ना? This is a part of NCERT. For inner portion, no charge inside, so E 0. For outer portion, it behaves like a point charge. Okay, so the field is kq by r square, where r is the distance of P point, r, capital R is the radius. So you already know that field would be something like this. Okay, for what? Ye. This is the actual sphere. This dotted is your imaginary Gaussian surface. Electric field where?
In the actual sphere.
Inside it would be 0 and outside it would be given by this. This you know already, right? Am I revising NCERT here? Am I helping you revise your NCERT? I definitely am not. So that's why I'm just discussing the result. I would be using them in some time. What about a solid sphere? Solid sphere. It has saman andar as well, you know, material andar. So for any point P, inside, the Gaussian surface is drawn concentric with the solid sphere but passing through P. Please note, you always need to take a Gaussian surface so that it passes through the point. It should pass through the point. So it is passing. So, you know, the field at P, the magnitude of field at P is same as magnitude of field at every other point on the Gaussian surface. The field at all these points would have same magnitude as at P, because it is on the surface of Gaussian surface. Is it okay? So here you can take the inner portion, you know, the field inside would come out to be KQR by capital R cube.
Sir, in Gaussian surface we take the charge enclosed inside Gaussian surface.
Charge enclosed inside Gaussian surface.
So P will be we are drawing on the point
Hmm.
Gaussian surface.
Hmm.
We consider it inside.
P point.
We are placing charge.
No, we are not placing. Dekho, actually this is a solid sphere. Whole of it is filled with charge. So you draw a Gaussian surface. P is any point. It's not a charge particle. It's any point. You want to check the field there. So we only consider the field inside, the charge inside.
So we can't otherwise put the charge on the
No, no, that would be a very typical problem of whether you want to keep it out or keep it in. Is it okay? Do I need to discuss it?
Yes, sir.
पढ़ के तो आते नहीं हो तुम लोग, इतना तो करके आना चाहिए था. The volume charge density for this sphere, if Q is the charge, it would be Q upon 4 by 3 pi Q, right? For inner portion, this is, it is a uniform charge density. So total charge by total volume is same as small charge by small volume. Sorry, the radius of the sphere is capital R, so it should be capital R, and this small portion, the charge on in small portion upon volume of small portion. So Q would be capital Q R cube by capital R cube. This would be the charge inside the Gaussian surface. Is it okay? Also you know that every point on the Gaussian surface has same magnitude of electric field. Why? Equidistant. Yeah. Okay. Same magnitude of electric field. So you have this. You have Q inside by epsilon naught, the Gauss law. Draw a small element. This is a small element. The field through this would be coming out, and the area vector would also be coming out. Okay? Gaussian surface is a closed surface, so area vector would always be outward. The angle between these two is 0, so we would write EDA cos 0, obviously it's 1, right? So it would be, now E vector is not a constant. Why? Because at different points the direction of E would be different, but E is a constant, the magnitude is a constant. Bring it out, closed surface. Here you are doing what? You are adding area of all the portions of Gaussian surface. So this is EA is area of Gaussian surface. So for Gaussian surface radius is R, it is actually E 4 pi R square, and it is equal to the charge inside Q inside upon epsilon naught. So R square, sorry, whole of this would go, 1 R would remain, E would be Q R upon 4 pi epsilon naught R cube, or KQR by capital R cube. The graph for this would be, this is inner portion, it would be like this. I used this. Till now I was calculating LHS. Now I used RHS. So for inside portion you can see E is proportional to R. Whenever E is proportional to R, the graph is a straight line passing through origin. Y is equal to mx type of graph. Straight line passing through origin. Okay, it is maximum at the surface. Outside the surface, let's say your point is here, the point is here x. At this point, for this point, the Gaussian surface would be like this, huge. Is it okay? So for this point, whole sphere can be considered as a point charge. You already know it. For outside points, the sphere behaves as a point charge. So the field would be like that for a point charge. It would be, this is inside, so outside it would be kq by small r square. Please note, small r is the distance of point from center, while capital R is the radius. So capital R is a constant, while small r is increasing. You are, moving away from the center, and trying to find field. So inside it was having this kind of formula, and outside it was having this kind of formula. So here, after you come out of the surface, the field drops rapidly like this, inversely proportional to r square.
In place of r, small r is
Capital R? Nahi. Small r is a variable quantity. So capital R is the radius of sphere. Small r is the distance of P from center. So P point was moving, is moving away like this. Graph is plotted like this. For a graph, you are increasing r, which means you are moving the point outward, and once the point comes out of surface, the formula changes. So in this formula as well, you would use small r itself. Flux would remain same. कुछ erase कर दूं? This is all you know. Okay. Now the fourth application, I don't know whether you know this or not. Okay. Oh, sorry, fifth. I was counting three. तो है, fourth कहाँ गया? Fourth was there. Fifth is hollow cylinder, long hollow cylinder rather. Okay, you have a long hollow cylinder of radius capital R. Is it okay? Okay. Okay. Now let us assume you have a point P here. Okay, for an inside point, what would be the Gaussian surface, shape of Gaussian surface? क्या होगी? हाँ, a smaller cylinder. Okay, but coaxial. So the Gaussian surface is a coaxial cylinder passing through P. But you know, as there is no charge inside, field would be 0. Since Q inside is 0, E is 0. So E inside is 0. इसमें कुछ दिमाग नहीं लगाना था. For outside point, let's call it X. For outside point, let's call it X. The Gaussian surface would be something like this. Okay, let us say L is the length of Gaussian surface and small r is the radius. Small r is the distance of point X. Okay. Okay. So Gaussian surface is a coaxial cylinder of radius small r greater than capital R. Okay, passing through x, नहीं x ले लिया है, q तो चार्ज के लिए यूज करते हैं ना. passing through x, comma having length L. Passing through L. So for this, it is a long cylinder, means total charge on this cylinder is not known. We just know the surface charge density. Cylinder is what? It's a sheet of material rolled. Cylinder यही होता है ना? Sheet of material rolled in the form of a cylinder. So it has a surface charge density sigma. Okay. So how much portion of the cylinder, the charged cylinder, do you need to consider? How much portion? I'll shade the portion. We have a red marker, luckily. So this portion you need to consider. How much is the length of this portion? L, right? L, not difficult. So, and what is the curved surface area? Because there is no charge inside, it is on the surface itself. So area A कितना होगा? 2 pi r, capital R L. Capital R is the radius of
the original cylinder.
Capital R is the radius of original cylinder. You need to consider area of original cylinder to find charge. So charge inside is how much? Sigma into area inside, right? Okay, this forms your LHS along with the epsilon naught. RHS is this. Okay, now just think. RHS is this thing. Okay, so now for the Gaussian surface, this is the electric field. Cylinder would produce field in all the possible directions, right? So this would be the electric field and this would be the area vector itself. यही होता है ना? So that's why we chose a cylinder, because all points of this Gaussian cylinder would be equidistant from our charge wala cylinder. Is it okay? All points on the Gaussian surface would be equidistant from the charged cylinder. So the field would have same magnitude everywhere on the Gaussian cylinder and the area vector would be parallel to the field. So it would be EDA. Again, since E is same at all the points on the Gaussian cylinder, we can bring it out. It would become E integral dA. E dA would be how much? Area of the outer cylinder, basically the Gaussian cylinder, Gaussian surface का area 2 pi small rl, and you know this is equal to q inside by epsilon naught. So E 2 pi rl is equal to sigma 2 pi rl upon epsilon naught. So 2 pi cancel, L cancel, E is sigma capital R upon epsilon naught small r. So E is inversely proportional to the distance, and the graph would be something like this, E versus R. For inside point E is 0, so here E is 0, and for outside it is inversely proportional to R. So at surface the distance is equal to capital R itself. So at surface the maximum value would be sigma by epsilon naught. Is it okay? At surface the maximum value would be sigma upon epsilon naught. Like this the graph would fall, and this the maximum value is E max is sigma by epsilon naught.
सही इस साइड वाला तो इन साइड वाले के लिए जब 0 है r is equal to r, जब हमने गॉसियन सर्फेस अनसाइडिंग दिए.
Is it okay? Actually it would be a dotted line. You know, you have studied discontinuous functions, discontinuity. You did discontinuity and you are denying. No, nahi pada. Discontinuous graphs. So this is a discontinuous graph. At this point it suddenly jumps to the maximum value sigma by epsilon naught. Which it has, but you cannot find it. It would have, but you won't be able to find it because the distance would be very small. E max, I'll tell you. So a student here asked that I took E max as sigma by epsilon naught on its own surface. For a point charge we cannot calculate the field on its own position, at its own position, while for a cylinder we calculated field at its own surface. Why? See, this there is a simple clear convention for all the uniform bodies that when you reach surface it simply means that you are just outside the surface. That's how you calculated this for a hollow sphere, for a solid sphere. Otherwise if you are at surface, how would you be able to clarify whether you are just inside or just outside? So for hollow bodies we assume, because surface is a very thin thing, when you reach surface you are just outside. So taking that assumption I calculated this, because just inside it would still be 0. Okay. So just inside the field is 0 and just outside it is sigma by epsilon naught. Okay, and the surface is very thin. So on the surface we always say the field is this. Okay. Shall I erase this? We need to do long solid cylinder. Okay. Or which one? 7th? Long solid. Okay. long solid cylinder, right? Okay, long means it is extended. Okay, it is all filled with material. Okay, one thing is sure, field inside won't be 0. Is it okay? One thing is sure, field inside won't be 0. For any point P which is inside, the Gaussian surface would be a coaxial cylinder of a radius small r, because the point is at a distance r from the axis. So here first portion is inside. Here Gaussian surface is a small coaxial cylinder of radius small r and length L passing through, right, passing through point P. Please note, a solid cylinder is filled with material, so it has volume, right? It has volume. So the charge density applicable to this situation would be volume charge density rho. The charge density applicable to this situation would be volume charge density. So now for where is the marker? For this surface, you need to consider this kind of charge, this portion only, the charge inside. So the charge inside would be how much? Density into volume inside, sigma into 4 by 3, right? Okay. And what about E dot dA? Yeah. Oh, sorry. I actually wrote the volume for a sphere. It would be pi r square L. Sorry, my bad. Now, consider a small portion. For it, the electric field would be coming out, symmetry, and the area vector would also be coming out, dA, right? So, you know, they are in the same direction, angle would be 0, we would be writing it as E dA integral, closed loop integral, of which E would come out. Do I need to explain why I brought E out? Symmetry, magnitude of E constant. So E vector is not constant, but E is constant. We brought it out. And this would become E into the area of this Gaussian surface. Which area? Only the only the curved surface. Only the curved surface of inner. Why am I not taking the flat surface? Because for a flat surface, this would be the area vector, while field would be like this. So I won't be taking the area of flat surface, only the curved surface, and it would be into 2 pi r L, and we know Gauss law is this. So it is E into 2 pi r L, which is sigma pi r square L by epsilon naught. L cancels, pi cancels, 1 r cancels. E would be rho r by 2 epsilon naught. E is proportional to r. So as you move away, electric field increases. As you move away, electric field increases. I hope you wrote it.
What
What
is inverse square law?
is?
Inverse square law.
Something is inversely proportional to r square. That is inverse square law.
So does it cos law is valid if electric field is not polarized?
No, then it won't be. Uh,
Why it is so?
See, Coulomb's law is an inverse square law. Means this. Means electric field would always be like this. The question here is that would Gauss law be still valid when inverse square law is not valid? Is it okay? ठीक है? Okay. Here we are multiplying E with area. The left hand term is independent of the distance, because this area would have r square type of terms. For a sphere, this area would have r square type of terms. This would come out to be independent of the distance. RHS is also independent of the distance. If E is not following inverse square law, LHS would be a distance dependent quantity. Violation would be there, distance dependent quantity, and this would be an independent distance independent quantity. So you won't be able to apply Gauss law, right? Can we continue? For outside point, right? I hope the Gaussian surface is clear to everyone. It is a coaxial cylinder, but of larger radius. So outside, for outside portion, Gaussian surface is a coaxial. Let's say this is the point x where you want to calculate the field. Is a coaxial cylinder of radius small r, comma length L, and passing through x, right? Passing through x. Now in this situation, how much charge do you think you need to consider? You need to consider only this much. Okay, so charge inside is rho into volume inside, which is rho into the length of this portion is L, and the radius is capital R. Radius of the cylinder is capital R, so it would be pi capital R square L. The RHS, the LHS would be this, and again by symmetry E dA, then E dA. So now you can do the same steps while you are sleeping, right? This 7th time you are repeating the same thing, 6th time. So E into the curved surface area, कितना 2 pi r l. Okay, so this thing, this is Gauss law, and this is E into 2 pi r l, and this is sigma pi r square l. So pi cancels, l cancels, E is sigma r square upon epsilon naught, I missed, by epsilon naught r, 2 epsilon naught r, sorry. Okay, so let's check out the graph. Till the surface, the field was increasing linearly, E was proportional to r, and after the surface it was falling inversely, right. We can find the maximum value. It would be, put r is equal to capital R here, the maximum value would be E max
Rho r upon 2 epsilon.
is rho r upon 2 epsilon naught. हो गया, done, करें आगे. So I'll erase this portion and I'll ask what JE asked few years back. The question was this: JE asked this. This is a long hollow cylinder, long solid charged cylinder of charge density rho, uniform charge density rho. Out of this, a sphere of the same radius r is cut. A sphere is cut of almost the same radius. Almost means the two parts are not separated. ऐसा नहीं कि नीचे वाला portion गिर पड़ा. This is not happening, right? So almost the same radius. So it means everywhere there is charge except for this hollow portion. A point just around the center, just near the center, in front of the center rather, P is here at a distance 2r, outside point. Now they asked how much would be the field now. Do you remember what I told you yesterday? Subtracting. Calculate the field for cylinder. This is outside point, we can calculate the field for cylinder and subtract the field due to a sphere. But there is a problem. Please listen to the problem. The problem is E due to sphere is how much? Outside point के लिए KQ by R square, Q by 4 pi epsilon naught R square. It is not in the form of charge density rho. So what you need to do is convert this.
Rho into 4 by 3 pi r cube upon 4 pi epsilon naught r square.
Right. So 4 pi go. So it would be rho r by 3 epsilon naught. This is for sphere. For cylinder, it would be abhi nikala, right? So rho.
Upon 2 epsilon naught. 2 epsilon.
Acha, sorry. This actually accidentally I took r, the distance to be capital R. It should be actually 2r. समझे ना क्यों? The distance is 2r from the center of sphere. I accidentally calculated the field at surface. Is it okay? Okay, so it would be 4r square,
Rho r upon
12r, बिल्कुल. 12 epsilon naught, and for a cylinder it would be rho r square upon 2 epsilon naught into 2r. Capital R is the radius of cylinder, it will not change, small r is the distance, which is 2r. So it would be how much? Rho r upon 4 epsilon naught r. So the net field would have been subtraction of these two, subtraction of these two. LCM तो लेना आता होगा. So rho r upon 6 epsilon naught. This was the answer, actual JEE problem. Okay.
सर सिलेंडर वाले में सिर्फ रो आर अपॉन 4 एप्सिलॉन नीचे आया नहीं देखो.
कौन से वाले में? अच्छा ये, हाँ ठीक है, ऊपर ठीक लिखा था. ओके, फाइनल आंसर ठीक है ना? ठीक है. Can we move? So it's time to say goodbye to Gauss law. Bye bye. Okay. Bye bye Gauss law. Let's start the next topic. Okay, we have spent quite a lot of time on Gauss law, but it had been a hot favorite amongst the JEE paper setters for quite some time. Okay, so you know, you may get a question on Gauss law. So I'll erase this, the right portion of the previous derivation, and now we start with a thing called electric potential. What is electric potential? What is electric potential? Yeah, this is the test charge Q naught. You bring it from infinity to point P. Let's say you do work infinity to P. So the potential would be infinity to P by the charge. And this is with the condition that limit Q naught tends to 0. Okay, the test charge is small. So we don't know the arrangement, it is just that we know that there is some electric field, we don't know the source, right? Okay, so for different sources the potential would be, I would tell you. You already know one more thing. What do we mean by spherical symmetry and cylindrical symmetry? And okay, spherical symmetry. A sphere, all points on it are equidistant from the center in all directions. Cylinder, okay, all points are equidistant from the axis. All points on the curved surface are equidistant from the axis. These are the two types of symmetries. Okay. So now for potential, let's go ahead. You already know that limit Q naught tends to 0. Work done would be F external dot S. Actually it is f dot ds vector and you integrate it upon q naught. यही होता है ना. Work done is what? This is the work done by you. Work done by you in bringing the charge from infinity to this point. So you are applying external force. The work done would be work done due to external force f external dot ds, right? And if there is a positive charge arrangement here, the test charge would be repelled. So you would be applying a force equal to the electric force but opposite in direction. So can I write this as limit q naught tends to 0 minus fe dot ds vector, ds or dr, it is same thing. Dr means change in position vector, which is displacement itself, right, upon q naught. समझ आया what I did? I just changed external force with electric force. Why? Because to move the charge slowly, here the charge is moved slowly, right? You are not giving any kinetic energy to it. So to move the charge slowly, you need to apply force just more than the electric force. So the external force would be slightly more than the electric force. We can assume it to be equal. But since the direction is opposite, I will take a negative sign here. Okay, I will take a negative sign here. Actually देखो, let's say the charge distribution is like this. You are bringing the charge to point P. This is point Q naught. So if now the position vector is R vector, after some time it would be reduced. It would be R minus dr vector. So you need to take care of the sign. Is it okay? Either you take care of the sign, or you can assume that for small portion the charge went outward. This would give you a positive dr, and while integrating you can take the limits reverse, that infinity to p, doesn't matter. Is it okay? Is it okay? That's what NCRT is doing. Let's move the charge outward so that we can have dot product easily, and then while taking the limits, we'll put the limits from larger distance to nearer distance, right? So from infinity to P point, or let's say R naught. Okay, that's what they are doing. So that is the best way actually to deal with here. Force upon test charge, this is what? Minus integral infinity to R naught. This is Fe by Q naught, limit here, limit Q naught tends to 0, Fe vector by Q naught dot dr vector, right? This whole thing is E. So V is minus infinity to R naught E dot dr. Is it okay? This is the mathematical formula for potential. Either you can use this or this. Okay, right? Potential difference is what? When you move a charge from point 1 to 1 to 2. So it is V2 minus V1 minus, again the limits would be, you are moving, this is the charge distribution, you are moving the charge from 1 to 2. So initial position 1 R1 to R2 E dot dr, again the same integral but the limits slightly changed. This is the potential difference. Is it okay? This is the potential difference. Okay, you already knew all this, है ना? Minus integral E dot dr होता है potential. Potential difference is actually same thing but with limits R1 to R2, not infinity to R. I am erasing the right half. Shall I erase? ये तो अब गया अब. convention. You always find out potential as well as electric field using a positive test charge. That's why the values come out to be positive. Okay. Had you been testing things using a negative test charge, then potential and electric field would have been negative near a positive charge. So since we somehow favor positive things a lot, positivity, so we use positive test charge, right? हाँ बोलियो उसको उठा के कैसे लाएंगे? You buy an insulating handle, fit the charge into the handle and move it.
But sir, it's very, very small.
Okay, very small. Okay. For it you need to buy some very good microscope as well. This all is imaginary. Why are you asking this? This all is imaginary. Obviously, you cannot have this. You cannot have the test charge to be 0. It would always have some value, some size. So, by this, it means that you should be taking a tiny charge. Obviously, you would be able to see it. छोटा लेना है लेकिन देख तो सको, right? So, this is not, even though this is the very accurate definition, but the value which we find from real world experiments is not that accurate. थोड़ा सा गड़बड़ होता है, but it's not much. Very small error, because you are taking a big charge. Okay. Can I raise this? Can I raise this? Now, to find potential due to bodies, there are two possible ways. Way 1 or 2. You can find if the formula, if expression for dV is easy, you can find potential by integrating dV. ठीक है? If expression for E vector is easy, you can use this. Two possibilities. I'll show you. Anyone is asking a doubt? Okay. For the right side, you know how to find potential for a hollow sphere, solid sphere, because the field for them is easy. The expression for electric field for them is easy, infinity to r pointile mark. Okay. The expression for electric field due to a hollow sphere is easy. The expression for electric field due to a solid sphere is easy, right? But the expression, but finding dV for them it is a task. नहीं निकाल पाओगे, difficult. Is it okay? So we go this for a sphere, both type, hollow, solid. We go this way for a ring. Okay, I will discuss both. Okay, not much needs to be discussed here. You already know a lot of things here. I just need to discuss the potential for a solid sphere, because not all of you would be knowing the potential for a solid sphere inside it. It's a little complicated expression. Is it okay? Can I erase it? Which one do you want to go for first? कौन सा पहले जाना है? Ring or sphere? Sphere ही करना पहले. Ring is smaller, easier. Let's go for a ring. Potential due to a ring. You do remember electric field due to a ring was a very complicated kind of expression. k q x upon r square plus x square raised to power 3 by 2. Difficult, right? So I won't be using it. P point. Let this be a ring of charge q. The potential due to this small element dq, this is radius r, this is x. Potential due to this at a point r कितना होगा? For a point charge, you know it is kq by r. So for a small element, dv would be k dq by r, k dq by under root r square plus x square. For v, you need to integrate. Only dq would be integrated. Why? Because this distance x is constant and the radius is constant. Okay, for all the portions. You take this portion, the distance x is still constant. Right? So k q by under root r square plus x square. That's it. Okay. So the graph for this would be an easy one. Let's say you have the ring here. Okay. At the center, when x is 0, the potential is how much? At the center, the potential is V max k q by r. R. Okay. And as you go away, potential would decrease. है ना? Easy.
अगर हम सरफेस से किसी भी तरफ जाएंगे तो दोनों तरफ मेरा डिक्रीज करेगा, हमने साइड वाला नेगेटिव में क्यों लिया?
नहीं, I didn't take it in negative. Potential तो पॉजिटिव रहेगा ना, it's a scalar quantity, डायरेक्शन तो होती नहीं. It is above x axis. The distance can be negative, right? Distance can be negative. मतलब the position can be on the negative x axis, position of the point. Can I erase it? I hope you have all done it. Potential due to a hollow sphere. Please note, potential due to a hollow sphere or electric field due to a hollow sphere are same as that for conducting sphere, because on a conducting sphere charge always travels to the outer surface. Okay, charge always travels to the outer surface, so you can easily understand that it becomes a hollow charge, hollow sphere, right? Inside there is no charge, even though there is a metal there, but it behaves like a hollow charged sphere. So it is a hollow sphere or conducting sphere. Same for electric field. Is it okay? Same for electric field. So you have this hollow sphere. Take a point P. I told you वैसे that the way we would be going is, we cannot find dV that easily here, because at this for this point some points are very close, some are little far, some are far, even more far. This point is the farthest. So for every point it would become very difficult for me to actually find the distances. So we cannot find dV. Is it okay? The way we are approaching it is minus E dot dr. So inside, for inside, you know V is minus E dot dr, but inside electric field is 0. So potential would be 0 कर दो सीधा, है ना 0 है ना constant. चलो अभी I'll leave it blank for a while. Let's discuss it outside. Infinity to R, and this would be minus integral k q, the charge is q, this is an outside point x, k q by r square into dr. Okay, positive sphere will release positive electric field, will the field would emit in outward direction, and we take dr in the outward direction as well. So dot product would become a positive value, and if you integrate it, I won't be doing it because you already know it for a point charge. The same kind of derivation, it is kq by r. Outside this value, surface value is kq by capital R, right? Kq by capital R. Surface value is this. Now let's discuss what would be the value here. Where the point where I discussed this, please write one more thing. E is minus dV by dr. E is the derivative, negative derivative of potential with distance, right? I just differentiated it. I just found dV and brought dr down. It's a dot product वैसे, which means it should be a partial derivative. Del V del R. Partial derivative पता है? You know in which topic it was taught? यहाँ पे हुआ है? नहीं? I'll tell you what is a partial derivative. So please write this there, the place where we found this. Okay, ये वहीं पे लिख लो. So now अब check this. Check this. From this you can understand as well. From there also I would tell you. E is 0. Derivative is 0. For which type of quantities derivative is 0? Constant quantities के लिए, maximum minimum के लिए भी, constant के लिए भी. So derivative is 0 means V is constant, right? Okay, inside the potential is constant. Now in our scenario, let's find out. This is an inner point. Field inside is 0 while field outside has a different function. So we would be splitting the integral into two portions. Infinity, you brought the point charge from infinity to surface, that was part 1 of your work done, and you brought it from here to point R, that was part 2 of your work done. Is it okay? So for part 1, the formula of electric field would be kq by r square dr. For part 2, the formula from capital R to small r. Part 2 समझ आ रहा है ना? From capital R distance to small r distance, from surface to inside, the formula would be 0 dot dr. So this would give me a 0 result, but this would give me the same result as the surface value. Is it okay? So V here would be same as surface value kq by r. I'll tell you how it happens. You brought the charge closer, the potential is increasing, you reached surface, the value would be this, and when you went inside, potential remains constant. How much? Surface jitna. Okay, the value of potential, the last value of potential was surface value. Is it okay? And inside it is constant, so it would be constant, it would have the same value as the surface value, right? Getting my point? As you move inside, the value remains constant, so it would hold the same value which it held last value जो थी surface value, it would hold the same value, right? So potential inside is the surface value and potential outside is KQ by R, right? You know the graphs. Can you draw the graph? The graph would be something like this. You know, the place is so crowded. I'll draw it here. nahi yaar, yahan, it's way too low. Can I raise this?
सर जो हो गया
ये हो गया ना? हाँ, I'll just erase the two lines. So, नहीं लिखी थी क्या? V versus R, inside it is constant till this is distance when you reach surface. Okay, this stands for surface point, after which it falls. V is inversely proportional to R. Here V is constant.
So the charges which we are centered on the surface, we are considering outer surface.
Outside. It is by convention. Whenever I say surface, you know, whenever I say surface, it simply means you are just outside the surface, right? Okay, somebody said why potential inside and at the surface is constant. See, I used this thing. Electric field is negative derivative of potential. Okay, negative derivative of potential. Please pay attention to this. Now, when electric field is 0, V should be constant. We already know that derivative of constant quantities is always 0. Okay, so now E is 0, it means V should be a constant quantity, right? So constant quantity inside, is it okay? The derivative is a constant, the potential is a constant quantity inside. Let's just check the values, how it would reach the same value. You bring the charge closer from infinity, your potential, the potential of the charge would increase using this formula. As R decreases, potential increases. When you reach the surface, potential is KQ by capital R, and as you go in, potential is constant. So constant means what? It would keep the same value which it held last. It would keep the same value which it had last on the surface, right? So it would have the same value inside everywhere. The graph would be a flat portion. Shall I erase it? Okay, हो गया सबका? And inside it is 0. Electric field would have value in outside the surface, but it would be 0 inside. See, I can understand you are getting confused कि surface का मतलब क्या? Inside or outside? By convention, what Gauss said, what other researchers, whatever, they said that by convention, whenever I say the word surface, for you it means the outer surface. For a sphere, it means the outer surface, not the inner surface. Whenever I say surface, it's the outer surface, because it's a very thin hollow sphere. For thick, it would have two surfaces, outer one and inner one. You would have to clearly specify. For a thin one, whenever I say surface, it means the outer surface. Is it okay? Okay, that's the convention that standard textbooks on electrostatics are following. Convention hai. And there is no rule behind it, but otherwise you won't be able to find. अब कभी अंदर लेना, कभी बाहर लेना, तो ऐसे मतलब इसका at times taking the point as inner surface, taking the point as the outer surface, a part of outer surface, it would make you confused, right? So we take one simple clear convention, outside surface. Whenever I surface, it's outside surface. What do you say? What do you think? What is the V max?
when we reach the surface.
It is the maximum value, but it is not a maxima point. Doesn't form a peak, right? It's not a maximum point. This is the possible maximum value bus. Can I raise this? है ना? कर दूँ ना?
Yes, sir.
Now this one is important. Please understand this. This has been asked time and again, once for electricity, once for gravitation. Okay, and again, they didn't ask the potential for a solid sphere. They asked a solid sphere is there, out of which a smaller sphere is cut out. Now tell us the potential at this point. And you know the process, right? Potential of the bigger body minus potential of the smaller body. Okay, so potential due to a solid, solid non-conducting sphere. Okay, potential due to a solid non-conducting sphere. Let's first go for the outside point. Okay, this is okay for outside point. Why? Because for outside point, field is very easy to remember, to recall. It behaves like a point charge, right? So for outside, again it would be difficult to find dV, right? Not easy. So we would be using again the same thing, minus E dot dr. Okay, so V is, let's say this distance is r here and the radius of the sphere is capital R. V is minus integral infinity to small r E dot dr. V is minus infinity to r, minus integral infinity to r, k q by r square dr. The field is away and the dr vector is also away. Okay, dr means change in r. It would be positive when you move away, it would be negative when you move closer. That's why we always take dr in the outward direction. We always move slightly in the outward direction, because in that situation we need not take a pain of considering the signs. If you take dr in the opposite direction, to what sara you need to take a lot of signs. So we ignore it by taking the dr in outside direction. So this is the arrangement, and this is quite like a point charge. This is like a point charge. So this would become kq by r outside. For surface, second would be surface. Vs would be kq by capital R. Right? Now let's discuss the inside point. V is minus infinity to r E dot dr. Okay. So just reach this point, till this point, because it would be a little tricky. Yo. The reason for x, some points are near, some are far, this is farthest, so many points. How can you find dV in this situation? It is easy to find dV only when there is a line. For line it was very easy, no? Ring is a line actually bent. For line it is easy, few points. For surfaces as well as volume bodies, it's difficult to find dV. So that's why you go the E dot dr way. Is it okay? I just told you na, that actually when you are moving closer, dr is negative. Dr is what? It is change in the position vector, and as you come closer, position vector decreases. So dr would be negative. I would be taking minus dr here. Plus, if you are moving it closer, electric field is opposite. I would be taking cos 180 degree. I would be taking negative signs twice, it would still give me the same thing. So I just got rid of all this. I consider dr in the outward direction. That we moved it slightly outward to find this, and then we integrated straight away. So this limit simply means that you brought it from infinity to r. It is the limit which decides kaise ho raha hai, right? So for an inside point, let's say this is the inside point P. कुछ नहीं करना है. For an inside point, you are bringing it like this and then here. Okay. Now please note, this is the distance r. The electric field has different formula for outside point and different formula for inside point. So I need to split this integral into two parts. One is when you brought the charge from infinity to surface, and then when you brought it from surface to inside. So I would be integrating it in two parts, and actually it won't need integration. One part won't need integration. It is infinity to r, infinity to capital R one part. This is E dot dr, okay, plus capital R to small r E dot dr. Got it? Okay. Infinity to surface point capital R, then capital R to small r. Is it okay? Now for this, for outside point, the electric field is like this. Please pay attention, don't write right now. For outside point, the electric field is like this. The integral will give you the value like this, but capital R in place of it because you reached surface. So for the first integral would actually give you kq by r. It would give you kq by r, and the second integral now we need to find. The second integral, electric field inside is kq small r by r square into dr, right? And now what? kq and capital R square are constants. kq and capital R square are constants. R dr would form R square by 2. So it's very easy now. R square by 2, capital R to small r. Okay. Let's put the limits. kq upon capital R minus kq upon R square. Okay, sorry, I made a mistake. It was r cube in the denominator. Please note. It was r cube in the electric field formula. So it's r cube. The r cube thing would remain, and this integral would become r square by 2 minus capital R square by 2. Now this has to be solved, and can you solve it? Please go ahead. You can take 2 common out of this, and you would have to take LCM. नहीं, it's a mistake. R square. R square plus it should be, actually you are taking 2 common. It should be 2. The result would be kq upon 2 r cube 3 r square minus small r square. Okay. Okay, shall I erase it? At least I can erase the left portion. Now this means this would have a fourth part as well. Potential is varying inside. It is not constant, it is varying inside. So in the fourth part, let's find it at center. At center, small r is 0. So V center would be kq by 2r cube into 3r square, or 3 by 2 kq by r. This is Vc. Vc is 3 by 2 Vs, 1.5 times the surface value. Okay, 1.5 times the surface value. Can I erase the right portion? Okay, कर दूँ ना? And let's check out the graph, and you would be amazed at the graph. I'll mark the point r is equal to capital R here. Okay, I'll draw only the positive portion. You can draw the negative. I'll extend it. I'll tell you what to do. At the center, V versus R. Okay, at center where distance is 0, the value is Vc is equal to 1.5 kq by r. Yeah, Vs. Okay, and for inside point, just think about it. Please pay attention. Just think about it. Whole of this thing is constant. Even this thing is constant. Only this thing is variable. V is of the form k a square minus x square. It is a quadratic equation with negative coefficient of square term. Means it would form a downward opening parabola. It would be a downward opening parabola till this point, right? Till this point. From this point onwards, the potential is, formula for potential is kq by r. So from now onwards, it takes a different shape. So here it's a downward opening parabola. Okay, and here it is inversely proportional to r. And on the other hand, on the other side as well, it will take the similar kind of shape. Right? Okay. Do you see a dhanush in it? Okay. Very good way to remember it. A dhanush shaped curve. है ना? ग्राफ एक्सप्लेन करो फिर से. The maximum value is at center. You already know this. This is 3 by 2 Vs or 3 by 2 kq by r. Okay. For inner portions, this is the formula. Okay. For inner portions, this is the formula. And you can check the first term, ये वाला bracket के बाहर वाला. The term outside bracket is a constant. Charge and radius of body will not change when you move inside or outside, right? Okay, this is the constant, even this is a constant, radius will not change. So it is of the form k v y is equal to k a square minus x square. It is a quadratic equation, okay, with negative coefficient of x square. And whenever coefficient of x square is negative, it's a downward opening parabola. So it would be a downward opening parabola from this point on the both sides. But till this point only. From surface onwards, it will take a different value, different formula. So it will fall like a rectangular hyperbola. So here the point is r is equal to minus r. Right? R is equal to minus r. On the negative side, on the other side basically. Right? But the value of potential would still be positive. Positive charge always gives positive potential. So Dhanush wala curve, right? And the time's up. Okay. So we'll discuss it later.